Okay, so 5.3 is on types of reactions. And we just have several of these that we're going to go through. When we did the Copper Cycle Lab, I talked about this a little bit, but this is basically where we are going to be with it, all right? Or this is where we're going to get into detail from this. So, in these, I'm going to use just some generic reactions where I have A, B, C, and D as my species involved. Okay. First of these that we're going to talk about is the synthesis reaction. Right? Synthesis means putting things together. So, A plus B react to form C. Okay. Here's a real-world example of that. Very simple reaction, but still a real-world example of this. 2H2 plus O2 reacts to form 2H2O. Right? That's a synthesis reaction. Now, the opposite of a synthesis reaction is a decomposition reaction. Right? So it could be... Actually, let me rephrase this. A plus B reacts to form AB. Because it's a substance just made from sticking those two things together. Right? So a decomposition reaction would be the opposite of that. AB reacts to form A plus B. Right? So we can take this reaction, do it in reverse. Now, if you think back to what I talked about in section 5.1 with spontaneity, this is considered a spontaneous reaction. Basically, we just kind of start this, we put enough activation energy into this, and as long as we still have these materials, they keep going. This one, we have to continuously put energy into to make it happen. But it will happen. 2H2O reacts to form 2H2 plus O2. All right. Now, your book, the next category of reactions your book talks about, or your book calls them exchange reactions. I learned these as displacement reactions. I try to be consistent and use the term your book uses, which is exchange, but just know that if you learn the term displacement, that's completely fine. Right? First of these, though, is the single exchange. Here's how this works. AB plus C reacts to form AC plus B. Right? Here's a good example of this. Let's say we have silver nitrate plus copper. That's going to react to form... Let me write this down on this line so that I don't run out of room. AgNO3 plus copper. That's going to react to form CuNO3 taken twice plus Ag. Now, of course, this is not balanced. Let's go back through and balance this. I believe that will have us balanced. That is a single exchange reaction, though. Right? Now, by the same token, let's look at a double exchange reaction. These sometimes are called precipitation reactions. All right? So we have AB and we have CD. They react to form AC plus BD. All right. let me bring our friend silver nitrate back into this. And I'm going to be good and put phase labels on this, which sometimes I get sloppy about. Silver nitrate, and so aqueous, meaning it's dissolved in water, plus NaCl, aqueous, reacts to form NaNO3 and AgCl, which is not soluble in water. So it's a solid. Now, if I were to do this reaction, I would mix these two things together and you would see this white cloud of silver chloride drop out of the solution. Right? That is a double exchange reaction. All right. Also in this, though, so those are our, and sorry, let me mention one other major reaction type, and that is the combustion reaction. Now, when we have a combustion reaction, we take something. Right? I'm going to use methane in this example. Oftentimes it's a hydrocarbon, but I'm going to use methane. We react it with oxygen, and our products always are CO2 and H2O. Now, if we have something other than carbon, hydrogen, and oxygen on the left side, then we get other products over on the right side. But anything we will talk about in this class, we're only going to be dealing with these three elements. And so this is always going to be our product. Or I should say, our products will always be CO2 and H2O. Okay, let's balance that one. Now, if I ask you on an exam question, and by the way, this is something I will ask you. This is another one of those times where I'm going to tell you to make a note that this is something that I mentioned in a video, just so I know you're watching this. Not that it affects your grade one way or another, but still, I like to know. If I say combustion of methane, just for example, all you do is you write CH4, that's the formula for methane, plus oxygen, reacts to form CO2 and H2O. And a lot of times when I ask you this question, I won't even ask you to balance it. So, about as easy as this gets. All right. Excuse me. Our last thing that we're going to talk about with this are reversible and irreversible reactions. All right. Everything we've talked about up to this point, essentially, we treat this as a reaction that goes to completion. All right? We mix the stuff together, we start the reaction, it goes to completion. But we can have these things called reversible reactions. Where, let's say just for example, we take NO2 gas, we put this in a sealed flask, and this will actually react with itself to give us N2O4 gas. Now, we can pretty easily observe this reaction because this has a dark reddish brown color. This is colorless, and so we can play with this and see what changes things. But here's the key with this, though. Constantly, this is reacting. NO2s are reacting together to form this N2O4, but it's almost as easy for these N2O4s to fall back apart and to turn back into NO2. So if we set this up, we put this in a sealed flask and we just leave it alone, we will get to a steady state concentration of these. And that state is called equilibrium. Equilibrium is a big topic. I spent 3 chapters talking about equilibrium in various different ways in Chem 142, which is Gen Chem 2. That's where equilibrium is not where these concentrations are equal, but where they are constant, right? And basically what that means is that this forward reaction is happening at the same rate as the reverse reaction. All right. That is section 5.3 for us.